we say that the integral domain R is a Prufer domain. If every finitely generated ideal is invertible. So an integral domain is a Prufer domain if every ideal that is finitely generated is invertible. Now remember, being finitely generated is a necessary but not sufficient condition for an ideal to be invertible. So what this is, what does it mean to be a Prufer domain? It means that every ideal that has a chance of being invertible actually is invertible. That's a way to think about it. So, examples. Well, how about this? Any principal ideal domain, right? Because what do we know in a domain? Every principal ideal, say generated by X, is invertible. Its inverse is generated by 1 over X, right? Okay, well, that's boring. These are also Dedekind domains. Okay, does anybody know a situation where the type of large class of domains where every ideal that is finitely generated is invertible? And if you want to come up with an example, think of a stronger condition than invertible. So what type of ideals do we know are invertible for sure? Principal ideals. So can you think of a large class of domains where every finitely generated ideal is principal? Right, you got more general. So the first thing I would say is any valuation domain. Because in valuation domain, all finitely generated ideal is principal. And somebody said Bayesian over here, and that's even better. Any Bayesian. Well, of course, now you might be a little upset because let me give you some more. So any PID in evaluation domain, the ring of entire functions. So I'll put these in your toolbox kind of for fun. The ring of all algebraic integers, the ring of all entire functions. These are also Prufer domains, but you might be a little disappointed in these ones because they're also Bayesian. So what's true in both of these rings, both of these domains, is any ideal that's finitely generated some type of principle. Can anybody, this one's a little trickier, I think. Can anybody think of an example of a ring that is a ring that is Prufer but not Bayesian?
That cheated a bit and like saw it, but like isn't it like some weird exotic thing like Z join negative 5 join Q? Okay, Q join negative 5 or something. Yeah, that. And if you join the forums, yeah.
So this is the set of Howard series over this field, which restrict down to the ring of integers constant. Right. This one should be Prufer, but not, and you can actually do this with any ring of algebraic integers in the quotient field. And I picked this one because this thing is actually a Dedekind domain that's not a Bayesian domain. So this thing right here actually has ideals that are finitely generated but not principal. So if you look at the ideal generator for 2 and 1 plus radical negative 5, that'll be an invertible ideal that's not principal. So actually, if you look at Prufer and Dedekind domains, there are about a zillion different. I think there's probably pushing 100 equivalent characterizations of Dedekind in the literature. I think there's a bunch of equivalent conditions for Prufer as well. So let me give you some of my favorite. Here. So what does it take to be a Prufer domain? What are the domain following conditions of equivalent? Number one, R is Prufer. Two, RP is evaluation. RP is second. And number 3, RM is evaluation. Well, and maximum. Okay, so here's kind of some warm-up equivalent conditions for Prufer. This is equivalent to saying if you localize at any prime, you get evaluation domain. That's really, this is really nice because locally it means, what this means is Prufer domains are stitched together. Locally, they're all evaluation domains, right, which are fundamental, and the Prufer domain is sort of stitched together through these localizations. And number 3, you don't even have to think, you don't even have to test it for all the primes. You only have to get the maximums. And let me tell you why. Certainly, if this is true, then this is true, right? Because if localization, every maximal is prime. So if this is true, this has to be true. Why is it true in the other direction? Well, because when you localize at a maximal ideal, these are sort of the smallest localizations. R localized at P can be bigger, right? For example, take P to be the 0 ideal, you've got the entire quotient field. And so if your evaluation domain, when you localize at every maximal ideal, any prime is contained in some maximal ideal. And this translates to an extension of evaluation domain, which is evaluation domain. So that's essentially it. Let me give you something a little bit more complete. Note. This is easy as all maximal ideals of prime. So let's do 1 implies 2. We want to, let's assume that R is a Prufer domain via our definition that every finitely generated ideal is invertible. And we want to show that R localized at P is a evaluation domain. So So suppose you've got your favorite proof domain, and let's suppose that you have a prime ideal. Consider we need to tell that R1 plus P is a valuation. Right, that's kind of a burden here. So, any ideas on how we can do that, or what characterization of valuation domains might be useful here?
Bit of visible condition.
What's that?
Bit of visible condition for any element.
I wonder if we can do that. But I think actually what we want to do is jump on something. Let me point out that recall V is the evaluation domain. It can only if V is quasi-local. That is, has a unique maximal ideal, and basic. Okay, well, note RP is certainly quasi-local. With the maximal ideal is P is generated by P. Now all we have to do is show that it's Bayesian. So got the quasi-local. Now what we need to do is show it's Bayesian. That is, we need to show that finitely generated ideal present. So let's let suppose that we have a finitely generated ideal. Note notice that must be a fractional ideal of R, right? It's finitely generated, so it's certainly fractional. So all I have to do is collect the denominators of those n things, and I can blast it back down into R. It's a fractional ideal of R, and so is invertible. In fact, if I use the element A to blast this back down in R, then A times this is invertible. And so this is invertible because you just take the inverse of that and multiply by A inverse. And so if you have an invertible ideal, I think we went over this. If you look, if I is invertible in R, then I localized to S is invertible in R localized to S. So this is also invertible. So this is an invertible ideal in a quasi-local ring. So it's principle. Because remember, over a quasi-local ring, you've only got one impact over a semi-quasi-local ring. If you have an invertible ideal, it has to be principal. Okay. So there we go. Okay. And finally, I think there's kind of shades of this in the next one. What do we got? We got 2 and plus 3, 1 plus 2. So I guess we need 3 and plus 1. So we've got this right here. We want to show the order of Prufer, so we need to show that every ideal is finite generated, or every finite generated ideal is variable. So left. I wouldn't call it the ideal. Well, this means that if you look at I, the ideal IM in RM is principal because RM is evaluation domain, so any finitely generated ideal is principal. So when you lift this finite generated ideal up to R localized M, you can find a single generator for it. Therefore, I finitely generated. Remember, this hypothesis is important. And I localized M is principal for all M and max. And remember, this is exactly the theorem we have. To give a finitely generated ideal, then and I am the principal for all my maximum ideals. So we've shown that every finitely generated ideal of R is variable. So R is principal. Any questions on that? Questions so far? Let me up the voltage on this a little bit. So we know that if R is Prufer, then R localized at any prime ideal evaluation. Right? Here's something that's sort of a convert. Let's suppose, on the other hand, that R is a Prufer domain with closure field K. If V is a valuation over R, then V is equal to R localized for some P in so here's the content of this. We already know that if you localize evaluation, a Prufer domain at a prime ideal, you get evaluation domain. This goes a step further and says, hey, not only that, but any valuation over ring actually is a localization. So that is to say, all of the valuation over rings are achieved by localization. Here's an example. Here's a non-example. So if you consider consider the polynomial ring fxy over a field of two variables. Its quotient field with rational functions and two variables over the field. Notice that this is not a Prufer domain. As the ideal generated by xy, which is a maximal ideal, but it's not invertible. In fact, I don't think any of the maximal ideals of this are invertible. And in fact, if this were Prufer, it would also be Dedekind because it's a theorem as well. But anyway, there exists a valuation overing of this. There exists valuation overing fxy, where and actually I can think of, let me give you a couple of them. In fact, I'm going to give you three. Notice that this is an overring of fxy. Localize it here. We've done this kind of construction before. This is evaluation overring. Notice what happens here is that notice that x divides y infinitely often, right? Because you have x and y in any valuation overring. One of them's got to divide the other. And here x takes the lead and it divides the crap out of y, right? You could also do a little role reversal here. And this one, you have that y sort of takes the lead. What's the other possibility? What's another possibility? So in the first one, I have a valuation overring of this, where x, the ideal generator of x and y survives, and x is basically the generator of the maximal ideal, right? And then you've got y that's sort of a lower echelon because it keeps being divisible by x. Then the next step, I've got y sitting as the maximal generator, and it divides x in a lower echelon. There's another possibility for the relationship between x and y, at least one more. What's that? Divide each other. That's right, without being units. So both y over x and x over y are in there, right? And they're both units, right? See if you can construct such a thing, but that exists as well. Yeah, and this one, I think this one's actually an theorem. You can get this theorem because you kind of squeeze out the y and the x. They come equivalent there. Right, so basically, in this case, what I've done is I've squeezed y and x together, right? And sort of both of them generate the max y ideal because they're associates to each other, right? In none of these cases are these valuations a localization, right? So this is a very strong condition here that every valuation over means, in fact, a localization of one of the prime ideals. Let's prove here. What did the evaluation over of R? And it's my one. I claim that V, so I've kind of given you a hint where I've written down. I claim that V is actually a localization of R. Any ideas what prime I will localize at, assuming that my theorem here is correct? Oh, that's right. I mean, it's the most natural thing to try. So let's see what happens. Let P. Of course, we know that in this max ideal evaluation over a P is just some prime that sits around an R. And I really hope that this is actually what I need here. Note, if S is an element of R minus, but not in P, then S inverse is actually in V. If not, then S is actually in the maximum ideal. So if you have anything that's in R but not in P, then it has to be outside the maximum ideal of V. Therefore, it's an invertible element in V. So because your denominators here are elements of S, and they're already units in V, so there's no harm in inverting them, right? So this containment is pretty smooth, no problem there. On the other hand, get the other containment. Note first, R localized P is a value. Because I know that R is Prufer in the first place. Let V be in V. We want to show that V is, of course, in R localized P. If V is not, then, of course, 1 over V is in R localized P. And here, of course, S is not in P. So in other words, if V is not in R localized P, then its inverse has to be in R localized P because it's valuation domain. So I can write V inverse as R over S, where S is not in P. So let's see what I get here. So S is equal to VR, right? And this I claim is in M. Why? Well, so, and this will be a contradiction. Why is it the case that this is an N? Well, where was V? V was in V, right? So notice that this is because, let me take this step by step, V is in N. The maximum will be. Because what happens if it's not? And V is a unit in V, right? And this means that, of course, that both V and V inverse are in R localized at S. They both have to be there if V is a unit in V. And so, S VR is in M, intersect R, which is P, and this is a constant. So it must be the case that B is equal to R. And so there you got your
but don't we already know that V has to be a unit in V? Because V is in V, and V inverse is in R localized P, which we showed was a subset of V.
Well, let's see. Let's see, did I go too fast here? So for the other containment, we want to show that V, so let V be in V. And of course, we know that the RP is certainly stated here. If V is not an R localized P, then V inverse is. Right, but we know that V inverse is, but if this is, so V must be a unit up in the big one, right? V is a V, its inverse is Well, so actually, so we can let me restructure this. You're right. I shouldn't have keyed on thing. So here we go. So we've got V and V. If V is, and of course we want to show that V is in our localized P. If it's not in our localized P, that means that V inverse is in our localized P. And you're right. Both V and V inverse are upstairs in the big one, so it's a unit up there. Right. So, note that as V is not in or plus P, then V inverse must be in right, the V inverse must be in is in the max plot. Of these all positive.
So the R's would be right.
Correct. Right. So V is because V inverse must be in the max ideal, because if it's not, then it's a unit, and that would mean that V is in this as well. Right. So V inverse is in the form P over S. There we go. That's a little better. With P and P and X none. Correct. So I can write as that fraction. And there we go. So this S equals PV. And this is in, S is in R. And PV is in M. Right. Because because P is actually an element of max quantity. So there we go. Yeah, thank you. I was a little bit sloppy the first time through. Okay. Any questions on that? Theorem. We actually had an easier proof before that if you have like evaluation overing, any overing of evaluation domain is automatic evaluation domain, because if you have evaluation ring, of course, K and some overring contains it. To show this one's evaluation domain, take anything in the quotient field, wherever it is X. Then because V is evaluation domain, either X is in here or X inverse, right? One of these two. And of course, that certainly has to apply to the bigger one, right? Because it contains that. So any overing of evaluation domain is evaluation domain. The same is true for Prufer domains, as a matter of fact. So if you're climbing, if you start with an ugly ring, I kind of think of this as mountain climbing, the mountain climber's eye, if you will. Once you hit the level of being evaluation domain, the higher you climb, you always stay in evaluation domain. Same as once you hit Prufer domain, you're always Prufer above that. Any overing of a Prufer domain. But RV Prufer domain. Then any overing of R is also Prufer. Okay, so let's see why this one works. Let's suppose that let R be Prufer and T an overing. What we have to do is show that T localized at any prime is evaluation domain. So let Q and so here's the strategy. Proof we need to show that T localized Q is a evaluation domain. And that's good enough to show that T is actually a Prufer domain. So let P be Q intersect R. R localized P is equal to T localized Q. And actually, this follows a sort of aphorism for what we did here. If you adapt this proof here, it'll work. And so, as R mod P is a valuation domain, so it is Q, and so PQ. Right, because the localization of the set here is just basically the complement of Q, just like we did the previous problem. Okay. All right. I'm going to probably leave at least part of this as an exercise here. Here. Be a domain. The following conditions are equal. Yes.
Final line of that proof. T is Prufer?
Yes. Yes, T is Prufer. There's no, so I mean the statement is correct, but it's not what you want. The following conditions are equivalent. R is Prufer. Two. Every overring of R is Prufer. By the way, not much so far, right? Because we've just proven this, and this is pretty obvious, right? If you consider R to be an overring itself. 3, this one I think is really cool. I almost guarantee I'll give you this one. Every overring R is infinitely closed. And 4, every overring is an intersection of localizations. Okay. All right. So let me talk a little bit about this. I want to let you go on some pieces of the puzzle. We just proved 1 implies 2. 2 implies 1 is easy, right? Let me point out like a little. Let me throw this in as a lemma. Any proof number is enclosed. This will help me actually connect the Legos here, right? If I know this. You might know why. then R that's no homework problem, isn't it? You don't need proof for that. Any integral domain is the intersection of localization of all the maximal ideals. Everybody okay with that? So this was this for line 2, you don't need proof for, you just need integral domain, right? But here's the important part. What can you say about these? These are valuation domains. And what do we know about valuation domains with regard to interval closure? They are integrally closed. So the upshot is a Prufer domain is an intersection of integrally closed domains. We know that any intersection of integrally closed domains is integrally closed. So that gets us right. So any Prufer domain has to be integrally closed. This helps me patch some things up. So, can somebody kind of outline 300 plus 4 now? Let me sketch this because I think I might kind of throw this in for it for homework. But let me talk about why this might be true. So you want to show that every overring is an intersection of localizations, correct? And the tool that you can use is every overring is integrally closed. Right.
Integral closure is the intersection of all the valuation domains that contain.
That is correct. Right. That's exactly the key that you need there. Right. So if you have an overring, say T is an overring of R, you know that T is integrally closed by statement 3. So it's an intersection of valuation overrings, all of which are localizations. Right. So this is kind of a neat one. This one I find this characterization fascinating because that is equivalent to Prufer is one, you hit the level where every overring is integrally closed. So in the Prufer world, as far as the mountain climbing goes, this also allows you to, when you attain Prufer, you're integrally closed, and you also have that anything higher is integrally closed as well. Okay, that's probably a good place for us to break for today. I'm sorry, I'll meet you guys on Wednesday, but we'll see you again by Friday. Any questions? All right, y'all keep it between the digits. We'll see you next time.